Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. Thank you so much for joining us here today as we begin our new unit on factoring and using factoring to solve polynomial equations. I'm very excited about this unit. It's got some of my favorite mathematics in it, so I'm particularly pumped to get started. Now, I will go ahead and tell you that this first lesson in this unit is a little bit lengthy because it creates a context for the entire rest of the unit. We're actually going to be looking at two different ideas and tying them together. Once we have those two ideas tied together in this lesson, the rest of the lessons in this unit should flow together pretty nicely. But just fair warning that what we're going to do here today is two separate ideas that we're going to be tying together to form one large idea. So it can get just a little bit tedious. It may veer off in a couple directions that might seem a little bit unrelated at first, but once we get going and we tie it all together, I think you're going to find that that it all works and seems to make sense. So you'll notice that there are two things identified here in our title today. The first is factored form. The second is solving polynomial equations. So those are the two big ideas we're going to have to look at today. Factored form and what factored form is, and then secondly, how does factored form help us solve polynomial equations. Two separate ideas. We're going to tie it all together. Hopefully, it's going to make some really good sense for you. So let's begin with this idea of factoring. Factoring is the reverse of multiplying, the reverse of multiplying. So when we factor an expression, it means we're going to write an equivalent expression that is the product of two or more expressions. And in earlier grades, we did this with factor trees. So what we're going to do on this first slide is we're going to talk about things that hopefully you already know. For example, if I said to you, please take 75 and write it in factored form. In elementary school, you probably would have taken 75 and would have said something to the effect of, oh, well, 75 can be split into 3 times 25. This would be an example of a partially factored form because it is written as the product of two expressions, the 3 and the 25. Of course, product meaning multiply. Now, it's not completely factored because 25 can be broken down into the product of two other factors. 3 remains a 3, and 25 can be written as 5 times 5. In elementary school, we referred to this as factoring to primes. And we said every number can be written as the product of prime numbers. In this case, 3 times 5 times 5. I know some of you have probably already thought, you know, 3 times 25 is not the only way to break down a 75. But if you look at that 75 and break it down differently, for example, 5 times 15, you'll notice that 15 is also not a prime number. The 5 would remain the same, but the 15 would break down into a 3 times 5. Notice that the primes that made the 75 when I use 3 times 25 and the primes that make the 75 when I do the 5 times 15 both ultimately end up being the same thing. Now notice, sometimes we write that as a list of primes, and then sometimes we take those primes and write them into a simpler exponent form. Rather than writing out all the 5s, we write it as 5 to the second power. Hopefully that is review for you. Hopefully it's something that you've seen before, not anything new or terribly overwhelming. But just to make sure, I'd recommend that you pause the video and try factoring a 63 to its primes. Can you take the composite number 63 and break it down into primes? I'm going to assume you've already paused the video and done that, so I'm going to go ahead and break it down. I would do this as probably a 7 times a 9. 7, of course, being a prime number. Right here, the 9 still being a composite number, because even though 7 can't be broken down into further factors, I know that 9 can be broken down into 3 times 3. Or sometimes you would write that as 7 times 3 squared. Notice that even though I used 7 times 9, you could have also done it as a 21 times 3 on this middle step, and it would have given you the exact same set of primes. In fact, every composite number has a unique set of prime factors. Here's one that's a little larger for you. I'd recommend pausing this and trying it on your own. If not, I'm going to assume you've already done that. I'll go ahead and work through this again. Since it ends in 0, I like to break this down into 10 times 27. That seems to me the easiest anytime something ends in a 0. Notice that both of those are composite numbers. The 10, of course, breaks into a 5 times 2. The 27 breaks into a 3 times 9. Notice that 5, 2, and 3 are all still prime numbers. And then notice that 9, of course, is a composite number and breaks down into 3 times 3. This is the unique set of primes that when multiplied together will give you 270. Now you can mix and match these lots of different ways to get different ways or different numbers in the middle. For example, we used 10 and 27. I could take this 10 and 3 and make it 30 times 9. I could do it as a 90 times 3. Lots of different ways to mix and match that, but no matter which of those I use, it is a unique set of prime numbers when we break it all the way down. Lastly, I want to show you this one, 18x squared y to the third. People freak out when they see the x squared and the y to the third, but honestly, I tend to ignore those and just deal with the 18. And then once I've got the 18, breaking down an x squared into its prime factors is actually very easy because it's just x times x. And breaking y cubed down into its prime factors is easy because it's just y times y times y times, did I get it? There we go, 3y's. And then if you wanted to write it in simplest exponent form, you would just put that back together, and of course you're back at x squared and y cubed. Again, this is not technically an algebra concept. These first examples over here are elementary school ideas. This we would consider probably a pre-algebra concept at this point. Certainly we could have talked about it in our exponent unit if we had wanted to, but it really leads in nicely to what we're wanting to do, which is factoring polynomials. A polynomial is in factored form when it is written as the product of its factors. For example, in the last unit, we talked about multiplying monomials times binomials. And when we talked about multiplying monomials times binomials, we said that whatever's on the outside gets distributed to everything on the inside, giving us a 5x plus 5. Notice that this right here is in standard form because it's in order by descending x to the first and x to the 0. This would be considered to be factored form because in factored form you have the monomial 5 multiplied by the binomial x plus 1. Now this plus sign tends to freak people out because it does say a product of factors, but remember that x plus 1 is inside of the parentheses, which means it's 5 times whatever number this whole thing happens to be. We just don't know what that number is. So this is factored form, this is standard form. And then we did some that were more complicated. We maybe had a linear monomial on the outside, a quadratic trinomial on the inside, and we distributed that negative 7x out to everything on the inside. This again is standard form. This is a cubic trinomial. This up here is factored form. You have the linear monomial multiplied by the quadratic trinomial. And then we talked about binomials being multiplied together, and we said that we can do this using the FOIL method, where the x gets multiplied by the x, and the x gets multiplied by the 1, and the negative 3 gets multiplied by the x, and the negative 3 gets multiplied by the 1. Again, if that's confusing to you, you may want to go back and watch that video. It's not our focus here today. But when we multiply that together, we get x squared plus 1x minus 3x minus 3, which simplifies to the quadratic trinomial x squared minus 2x minus 3. Notice, this is standard form. This is factored form because it's a binomial multiplied by a binomial. Standard form and factored form. Now, before we were taking things that were in factored form and multiplying them together to put them in standard form, because there's a lot of times where having something in standard form is more useful to us. But there are other times when having things in factored form is more useful for us. That's what this unit is going to be about. It's going to be about taking things that may or may not be in standard form and moving them into a factored form in order to help us solve equations. The first thing we have to be able to do, though, is we have to be able to recognize which things are in factored form and which are not. So when I look over here, I have x minus 5 times x plus 3. Is that in factored form? It is. Notice it's a linear binomial times a linear binomial. Yes, this is factored form. What about this one? This is not in factored form. Notice that it is a linear monomial added to a constant monomial, or you could make the argument that this is a linear binomial that's not multiplied by anything. How about over here? Is this in factored form? Yes, it is. You have a 5x multiplied by a x minus 4 multiplied by a x plus 9. Notice whatever value this is multiplied by this, which is multiplied by this. How about over here? This is not in factored form. When you look at it, it looks like it at first. This is 11 times x minus 9, but notice you've got this plus 5 on the end, or this minus 5 on the end. You can't do that. It has to be everything multiplied together. If there are any additional multiplications, or any addition or subtraction symbols, they need to be inside of parentheses so that they are a product as a unit. How about this last one? Hopefully you recognize that is standard form. You've got this added to this added to this. Does that make sense? Okay, that's the first of our two big ideas. That is factored form. It is polynomials that are multiplied together, or it's a product of factors. I'm going to take you to the second big idea. It's going to seem completely unrelated, and then we're going to tie the two together in just a second. Why do we like things in factored form? Well, consider this. The zero product property says, if I have 5 times 0, that product is 0. If I have 0 times 9, that product is 0. If I have 0 times a binomial, I would distribute the 0 out and get 0x plus 0, which is 0. And if I had a quadratic trinomial times 0, I would distribute the 0 out. I would get 0 times 4x squared is 0. 0 times 5x is 0. 0 times negative 7 is 0, which gives me 0. In fact, this is a rule you probably learned very, very early on in your mathematical career and probably understand it pretty intuitively now, and that is that 0 times anything always equals 0. Now, I happen to really like this property because it seems kind of obvious, and it almost seems to be on the nose to be saying that anything times 0 equals 0 in an algebra class because you've known it for so long. But this property allows us to do some very, very cool things that we may not realize. And so I'm going to say it a little more formally this way. If I have a number x multiplied by a number y, and the solution is 0, that means one of three things must be true. Either the x is a 0 and y is a different number. 0 times 1 is 0, 0 times 2 is 0, 0 times 18 is 0, 0 times negative 8 is 0, 0 times radical 50. If x is a 0, it doesn't matter what y is, the solution will always come out as a 0. Conversely, if y is a 0, it doesn't matter what x is. This could be 10 times 0, 11 times 0, negative 80 times 0, 54 million times 0. No matter what x is, if y is a 0, our solution comes out as a 0. Or the last thing that could happen is that they could both be 0. Notice my little typo here. This should say x equals 0 and y equals 0. See if I can fix that for you real quick. X equals 0 and y equals 0, because 0 times 0 is equal to 0. Let's tie this all together now. This is really going to be cool. I love this. If I have something written in factored form, notice the left side of this says x times the quantity x plus 7 equals 0. If I have any product or anything in factored form equal to 0, this tells me a couple things that must be true. Either the first thing must be a 0, or the second factor must be a 0. One of those two things must be true in order for us to get a 0 as our solution. If x is a 0, 0 times whatever this would be 0. If whatever's in parentheses comes out as a 0, it doesn't matter what's up front because this times 0 equals 0. Well, x equals 0 obviously tells us that x equals 0, but I can also use the property of equality and subtract 7 from both sides of this equation and get x equals negative 7. In fact, this equation has two solutions. X is either a 0 or a negative 7. Either one of those will make the statement true. Now, just for the sake of having it in our first example, since there's two equations, I need to check them both. We always rewrite the original problem, substitute the value in that we want to check, for example, 0, so I put a 0 in for x, and we simplify to see if the sides match, and they do. Since there are two solutions, I need to check them both, so I rewrite the original equation. This time I'm going to plug in the negative 7, and then I simplify to see if I can get the two sides to match. Negative 7 plus positive 7 is 0. Negative 7 times 0 is 0. Both of these will work. You see, if something's written in factored form and it's equal to 0, I can solve this very easily just by setting each of the factors equal to 0. Makes this very, very easy to solve. Also, if I make them look more complicated, it doesn't really matter. Notice here I have a linear binomial times a linear binomial. It is in factored form. This number gets multiplied by this number. So using the 0 product property, I know either the x minus 3 has to be a 0 or the x minus 8 has to be a 0. Both of these are simple equations I can solve using the property of equality. If I add 3 to both sides, I get x is a 3. If I subtract 8 from both sides, I get x equals negative 8. And there are your solutions. Now, once again, I can check these. I rewrite the original equation, put a 3 in for my x, the sides match. Or I can write the original equation, stick a negative 8 in for x, and both sides match. Notice in the first example, the first term became the 0. In the second example, the second term became a 0. It doesn't matter which of these is a 0, as long as one of them is a 0, I know my answer will come out as 0. Isn't that cool? I like that. This is just a set of 4 of these. I'd recommend pausing the video, trying these on your own. I'm going to do them fairly quickly, and then you can pause the video to see the worked out solutions if you want to, but I don't want to take up a whole lot of time on this because I think you'll catch on to this pretty easily. The first example, either the x is a 0 or the x minus a 1 is a 0, meaning your solutions are 0 or 1. Notice I'm not taking the time to check that. You can do that if you like. In the second example, either the 3m is a 0 or the m plus 2 is a 0. That means if you divide both sides by 3 on this one, you get m is equal to 0. If you subtract 2 from both sides on this one, you get negative 2. Coming down to here, either the z minus 4 has to be a 0 or the z minus 6 has to be a 0. Using your property of equality, you can add 4 to both sides and get z as a 4, or you can add 6 to both sides and get z as a 6. There's your solutions. And notice down here, you have 1, 2, 3 factors. If any one of those is equal to 0, this will come out as a 0, which means x can either be a negative 1, x could be a positive 3, or x could be a positive 2. Any of those are solutions to this equation. Isn't that awesome? I love that. Here again, here's another set. I made them look a little different, a little more complicated, but the idea is basically the same. If you feel pretty comfortable, you can go ahead and work it out on your own, pause the video, and then watch my solutions or skim ahead if you want to save yourself a little bit of time. This first example, notice that it's x minus 4 times x minus 4. Both of those have the same solution, so this would just be 4. In the second example, 2x plus 3 is 0, x minus 6 is 0, or 3x minus 4 is 0. The first one here, again, I'm not going to take the time to solve this out, but you can use your property of equality to subtract 3 from both sides, divide both sides by 2. If you're struggling with that, you need to go back and watch our solving equations video back from first quarter. The second one, x minus 6 equals 0. I'm just going to add 6 to both sides. Over here, I'm going to add 4 to both sides, divide both sides by 3, and you get x equals 4/3. And the next one, I just changed to a z from an x. Doesn't really matter. And the last one, I do want to point this out. Oh, wow, I almost screwed up, didn't I? This is 1 or 11. Make sure you get both of them down. This one's interesting. Either negative 7 equals 0, x minus 3 equals 0, or x minus 2 equals 0. Notice that negative 7 equals 0 doesn't make any sense. That's just a nonsense statement, so we're going to ignore that. I always take the time to write it out, though, because if this had been an x on the outside, x equals 0 would have been an acceptable solution. Then we just solve the other two. That's not bad, right? Okay, let's make it a little more challenging. If something is not given to us in factored form, that's where the work of this unit comes from, is how do I get it to be in factored form if it was not initially in factored form? We're going to learn several methods for doing that, the simplest of which we're going to talk about today, and that is factoring out the GCF. Factoring out the GCF. Notice, this is a quadratic binomial. I want you to think of it as being the answer to a multiplication or distributive property problem. We would have solved this in our last unit by taking whatever's on the outside and multiplying it by everything on the inside. We said before that this form is factored form, this is standard form. Now, here's where you've got to use your imagination just a little bit. You've got to stop and think about when you look at this term and you look at this term and you ask yourself, what do those have in common? Or what could possibly have been multiplied by both of those? Hopefully you recognize that both of these have a 3. In fact, if I can identify that both of them have a common factor of 3, I can pull that factor out and realize what the original problem was. The first value is 3 times x squared. That's 3x squared. To get the 3 on the end, I had to do a 3 times 1. This is called factoring, taking something that's written in standard form and changing it back to factored form. Or I should say this is algebraic factoring. How about this? Can you look at this and see if you were to look at both of these terms and you were to think back to our last unit where we were multiplying something on the outside times everything on the end, what do these two numbers, 4 and 24, have in common? Hopefully you realize both of them are divisible by 4. And if you look at the x's, this has 4 of them, this has 3 of them. In fact, they both have at least 3 x's. This is the greatest common factor of these two monomials, or of each term in the binomial. I can pull that out and write it in factored form. That GCF goes on the outside, and I just ask myself, 4x cubed times what gives me 4x to the 4th? 4x cubed times what would give me 24x to the 3rd. See how that works? I'd recommend pausing the video and trying this one on your own. Again, you're looking for what can I pull out of the 2x squared that I can also pull out of a 20y cubed. Hopefully you realize they both have a 2 in common. So I'm going to pull that 2 out. 2 times x squared is 2x squared. 2 times 10y cubed is 20y cubed. How about this one? Is there something that all three of these terms have in common? Well, it's easy to see they all have at least one x. At least one x. Can you see a number that can go into 8, 20, and 12? A lot of people say 2, which is correct, but remember, I want the greatest common factor. There is something bigger than 2 that will come out. It's actually a 4. I'm going to pull a 4 out of this, but because the leading coefficient is a negative number, I'm actually going to pull out a negative 4, and then I'm going to pull out x to the first power. The reason for that is 3 is the most x's followed by 2. The fewest x's that any of these have is the 1. That means it's the most they have in common, 4x to the first. Now, the reason we pull out the negative 4 is because it does make the leading coefficient of this trinomial into a positive number. I can't really explain to you why that's important today, but it is very, very helpful for you in what we're going to do over the next several days. So make that a habit. Pull out that negative 4 whenever you can. Here's one more. Can you think about what these have in common? If you're not sure yet, go ahead and pause the video. I'm going to keep going. They both have 4a squareds. 4a squared. 4 is the largest number that goes into 16 and 20. They both have a squared, so I can pull that out. This one has a b squared, but this one doesn't, so I have to leave it alone. Remember, I can only pull out the things they have in common. Notice 4a squared times 4b squared is 16a squared b squared. 4a squared times 5 is 20a squared. Now, we've got these two big ideas rolling around. This factored form and using the zero product property to solve, and then this idea of putting things into factored form. We're going to tie it all together now. If I were to ask you to solve something that looks like this, 2x squared plus 8x equals 0. Ordinarily, this would be very difficult for us because we cannot add these together. They're not like terms. If I were to subtract 8x from both sides, now I've got x's on both sides, which becomes more difficult. Instead, whenever you've got something like this, you're going to want to write it into factored form. So ignoring the equals 0 for a second, and just looking at this left side, what would that look like in factored form? What GCF could I pull out of a 2x squared and an 8x? Well, they both have 2 x's. 2x times x makes 2x squared, 2x times 4 makes 8x, and it equals 0. Notice right here, this looks like the ones we solved earlier. You've got 2x multiplied by x plus 4. This is factored form. The zero product property says in order for that to equal 0, either the 2x is a 0 or the x plus 4 is a 0. Which means if I divide both sides by 2, this is x equals 0. I subtract 4 from both sides, that equals negative 4. Notice that I'm showing fewer steps as I'm going along. That's out of respect for you because I don't want you to have to sit and watch me do that every single time if you're already comfortable solving those smaller equations. Over here on the right, can we write this in factored form? I'd recommend pausing the video because I'm going to go ahead and show you what the answer is. Both of these have 2n. 2n times 3n plus 5 equals 0, which means either the 2n is a 0 or the 3n plus 5 is a 0. And again, you would work that out and solve it. You get either 0 or negative 5/3. Subtract 5 from both sides, divide both sides by 3. How about down here? I would factor out the a. Either the a is a 0 or the a plus 5 is a 0. And you get 0 or negative 5. One thing that's important to mention is in order for this to work, one side must be set equal to 0. I would write that off over to the side. I would do it for you right now, but it would take me forever to do that using my mouse. So make yourself a note on that if you're taking some notes that one side must be equal to 0. The other side must be written in factored form. 3x times 2x minus 3 equals 0. That means either the 3x is a 0 or the 2x minus 3 is a 0. We solve both of those and we come up with 0 or 3 halves. That's the basic idea for today. Now, it is convenient for us that all of these do have a GCF, and when we pull the GCF out, what's left is a linear binomial and a linear monomial. Notice linear, linear, linear. Once they get down to a single variable to the first power, they're pretty easy for us to work with. That is not always the case, and as we work our way through this unit, we're going to deal with more and more complex equations that are more difficult to put into factored form. For the moment, though, we're just focused on factoring out the GCF. I do have one more slide for you. I want you to take a look at this. I actually pulled this out of an old textbook. It says you can model the arch of a fireplace using the equation y equals -1/9 times x minus 18 times x plus 18. If you've followed along with us all year, you'll notice that this fireplace is a parabola. We've dealt with parabolas quite a bit. And in fact, if I were to take this, which is already written in factored form, and I were to multiply it back together to standard form, you would find that it is a quadratic trinomial with a leading coefficient that is negative. Notice that once it's written in factored form, if I want to know how far this base is, I just need the distance from here to here. Well, if I solve the equation, -1/9 equals 0, x minus 18 equals 0, and x plus 18 equals 0. Notice the first statement is nonsense. This one gives me an x of 18, and this one gives me an x of -18. Some of you are probably asking, how did you know they equaled 0? Well, if you're looking at this base, notice all of these are along the x-axis, which means for all of those, the y-coordinate is going to be 0. So I'm just plugging 0 in to find where or which x values give me y equals 0. And we found that when x is 18, y is a 0. And we found that when x is -18, y is a 0. And can I get that? Maybe. That's hard to draw. Sorry about that. Notice I still have not answered the question yet. The question is, how far apart are they? Well, if you want to find the distance between two things, you're looking for the difference between them. So we subtract, and you get 36 inches. Now, people often ask me, how do I know that my parabola is actually on the y-axis? Well, because I can stick it wherever I wanted to stick it for the most part. We could have slid the entire graph over, and we could have had the top of our fireplace way over here at what is that, is that 15, something like that. But I don't know why you want to do that when it's much easier to write equations if your vertex is on the y-axis. So that's just how we chose to do it. Hopefully this has been helpful to you and not too overwhelming. As I mentioned, this is an introductory lesson. The others will not be quite as overwhelming. I think if you did have some trouble, you might want to go back and watch it a second time. Focus on the two big ideas separately and then tie it all together at the end. I think it'll make a lot of sense for you. As always, I do wish you the very best of luck. Thank you so much for taking the time to watch this video with us. Make sure you hit that like button. Make sure you subscribe, turn on your notifications so that you don't miss any of the exciting things coming out of Nunley Math. Best wishes to you all. Take care.